are going to talk about a tree traverse algorithm, an in-order recursive algorithm. So many times it gets asked in interview questions, but it's also a favorite of Googlers, and specifically it's a favorite of Googlers. And what makes this one special is that it doesn't require any extra space. It doesn't require any extra space, unlike a typical recursive algorithm. So there is this tree that I want to give you an example of. So we are going to traverse a binary search tree, which means every right child is greater than the parent and the left child is less. And in order traverse will give us a sorted number in the list. So if you look at the in order, what we want to do is look at all the left child first, then the parent, then all the rights. And it's the same thing in every subtree. So in this subtree, look at the left first, then the parent, then the then the right. But if you think about it, when I'm at the roots, I have to go down, down, down to come here and then traverse this first and then somehow go back up. But because I don't have a link to the parent of each node, there is no link to the parents. So this doesn't exist in a typical data structure. That's why there is a challenge of, if I'm here, how can I go back up? So the predecessor of any root is, we are going to look at the left subtree and we will go to start from the left child. At this point we will go right if it has even one more child. If it has 5, let's say if it has 5, the predecessor would be 5, because starting from the left child we go right until we reach to the end, until we reach to something that doesn't have any more rights. And the reason is that this will give us the greater number in this left subtree. So the predecessor is the greater number in the left subtree. The challenge here is that it would be really great if we had a link between the predecessor and this one, because we know after this predecessor it comes the root. Imagine that this is our tree that we want to traverse in order. And because there's no link to the parents, if I'm down here, there is no way that I can go back to the top. And so every parent, they need to process the left first, then the parent, then the right. So in order to do that, there is a way that if at any subtree, if I'm at this subtree, if my pointer is here, I'm going to look at the left subtree and see which one is the most, which is, and this 4 is 4, which is the predecessor. And because there is no more right, I can make a temporary link to this to come back. So at any point, I know that 6 comes after 4. So if I come to 4, I know how to go back to 6. Then at that point, I will delete the pointer. I will go back to 3. So because it also has a left child, I'll do the same. So the predecessor of this left child is itself. So there is a link from the itself to 3. So my pointer goes back to 1. There is, at this point, because there is no child, I can just print this and go to the right, which is number 3. I'm at number 3 and there is a left child, so the predecessor of the left child goes back to 3. So at this point, I know I already processed the left child, and I can just take pop 3 and go to the right. So my pointer goes back to here. This one doesn't have any left, so I can just pop it and go to its right, which is 6. I'm at 6. The predecessor of this, and I have a left one, but the predecessor of this subtree is 6. Because I've done that, I know that I already processed the left side, so I can just pop 6 and go to the right. So, and I'll keep doing the same process over and over again. So the idea here is that I would have a link from the subtree, the left subtree, the greater number in the left subtree to my parent, because that's in order. And so continue. So first things first, we need to have a binary search tree, and I only want to write an API for it, only the very simple and basic one. So I only want to have an add so that I can add some items. And let's say I will come back and complete this later. And now I can have a just binary search tree or processing class or something like that, where this is also an API for this class. I'll get a binary search tree and then I'll have it here. Just the binary search tree. And the method that I'm interested to have is just maybe in order. So I created a BSD here and I add 6 first. So 6 would be the root. Then I add 3. 3 would be the left of that root. 8 would be the right of my 6. 1 would be the left of 3. And so on and so forth. It will be the same as our example in the video. And I want to be able to create a BST processing object with my BST, passing my BST into it, and then call in order method. And I want to create it as a generator so that I can call a for or iterator on it and then print it every time. I obviously need to have a method for predecessors of a node. And let's say we completed that. We can always come back and complete this, but for now, I just assume that I already completed that. I will have a pointer to the first node, which is the root, while this pointer is not none, because it will eventually it will get none. While this is not none, go find predecessor. Predecessor would be the self.predecessor, which calculates the predecessor of my node. And if the predecessor equals to my node, or the predecessor is none, then go to the right. It means in both cases, it means I don't have any more predecessor and I'm done with my left. So first I can just yield the data, walk the data, and then walk equals to walk dot right. But otherwise, it means I'm not done with the left. So else, I'm still not done with the left, so the walk will be walk dot left. But before doing that, because I already found the predecessor, right, and I want the predecessor, the right, to be my node, the node that I calculated the predecessor for. I want its right to be point back to it. Yeah. So this one obviously doesn't work because our BST, it doesn't even have like self the root equals to none. So this one, it says it's worked, but obviously it doesn't have anything to show because the add method is empty. I can just fill it out, just copy and paste my code. Before I even start with binary search tree, I have a node class that I can pass the data, and then I can set its left and right method. A private function that finds a good spot for my new node to be added. Just a placeholder of that node. Yes, and it works. It printed for me 1, 3, 4, 5, 6, 8, and 9 in order. This is super interesting because as you see here, I am not using any extra space because I'm not using recursive method, which takes up some more space. It uses a stack. I'm only moving my pointer, which is my walk, into different points at each time, and I'm only using a while, which at every time it points to a different place, but I'm not keeping track of any previous parents or any other things that I need to keep track. And this way I'm not using any space. I'm using only the pointers of the predecessor to go back to my parents or my grandparents so that I can have them whenever I want to. At this point or at any of these points, you can also, if you want to preserve your BSD, you can also get rid of those extra pointers at some point. And what makes this one special is that it doesn't require any extra space, and it's not